Hello everyone. We ended the last class where we derived an expression for the characteristic rate of strain. As you see on the screen, L squared mean is this expression here, AF times C epsilon to the 2/3 and delta to the negative 4/3, where AF is given by this expression. I did say we'll come back to this later, but keep this in mind. This is an expression for the characteristic rate of strain, and this was a development started originally by Lilly in 1967. Okay, so we'll come back to this after we actually filter the equations, and that's what we're going to do today. So just like we did the Reynolds decomposition and derived the Reynolds equations for RANS-based approaches, here we are going to derive the filtered conservation equations by doing a filtering operation onto the Navier-Stokes. So we will consider spatially uniform filters so that the filtering and differentiation commute. So the filter itself is not a function of space. We are originally starting with the continuity equation and we filter that equation, isn't it? So keep in mind that U is equal to UI bar. UI is equal to UI bar plus UI prime, which is the residual field, isn't it? So you consider the continuity equation and then you filter it. Obviously, the filtering and the differentiation commute. Then what you get is del xi of ui bar is equal to 0. What does that tell you? That means the instantaneous velocity is obviously satisfying continuity and the filtered velocity is also satisfying continuity. Now, if you take a derivative of the residual field, so del xi of ui prime, that would be equal to del xi by definition would be ui minus ui bar, right? Ui minus ui bar. And this is going to be equal to 0, isn't it? This is going to be equal to 0. Why? Because your velocity field originally satisfies continuity and your filtered velocity field also satisfies continuity. So that way, this and this, both of them equate to 0, and that is why you get 0. So this means what? This implies that the residual field also satisfies continuity, isn't it? Ui prime satisfies continuity. So essentially, the conclusion is that the instantaneous field obviously satisfies continuity. We knew that already. The filtered field, velocity field, and the residual field also satisfy continuity. That is what we get from the continuity equation. Now let's move on to the conservation of momentum. So we start with the filtered momentum equation, and what we do is we take the momentum equation and then filter each and every term. So the time derivative and the filtering operation commute. So then you have del t of uj bar plus del xi of ui uj bar, and again you are commuting the filtering operation and the differentiation operation. So essentially you are just taking ui uj bar, and then you have the viscous term, which is nu del squared del xi squared uj bar minus 1 over rho del xj of del p bar. Okay, so everything is pretty clear. The p bar is the filtered pressure field as well. Now keep in mind, this is going to be a different equation from your from the Navier-Stokes equations, mainly because this term is not the same as ui bar times uj bar, isn't it? Ui uj bar is not the same as ui bar and uj bar. All right, as much as the filtering and the differentiation commute, this is not the same. Okay, so that's what we mean by the filtered product is not the same as the product of the filtered velocities, isn't it? So now what does that mean? So let's say you define what is called a residual stress tensor, okay, and I'm calling it tau ij with a superscript capital R. Tau ij superscript capital R would be equal to the difference between the filtered product and the product of the filtered velocity. So ui uj bar minus ui bar and uj bar. Let's call that the residual stress tensor. Now this is analogous to the Reynolds stress tensor, which we had shown earlier, which is ui uj mean is ui uj mean minus ui mean times uj mean. Remember, this is the fluctuation. Okay, this right here is the mean velocity, right? So it is the actual velocity product and then mean. So ui uj mean minus ui mean and uj mean. Fine. Now let's define what is called a residual kinetic energy, and let's call that Kr, which would be equal to half tau I capital R. And you can see that. So tau I j capital R is defined here, and that is your residual stress tensor. If I make j is equal to I, then basically what I'm taking is the trace of that residual stress tensor, isn't it? I'm taking the trace of the residual stress tensor. That would be tau 11R plus tau 22R plus tau 33R, and half of that, right, half of the trace would be equal to the residual kinetic energy, wouldn't it? So we call that Kr, which is half tau I capital R. And now what I'm going to do is, just like I did earlier with the Reynolds stress, I am going to be considering an anisotropic residual stress tensor. So tau ij small r. Tau ij small r is this tau ij capital R minus 2/3 Kr delta ij. So what am I doing here? I am taking the anisotropic part of the residual stress tensor. What I'm doing is I'm separating out the isotropic part, which is the trace, and the anisotropic part, which is the non-diagonal components. And so how am I doing that? The tau ij small r is the anisotropic part. That would be equal to tau ij capital R minus 2/3 Kr delta ij. Minus 2/3 delta Kr, 2/3 Kr delta ij. So that would be, again, just to make you understand this a little bit better, that there is a reason why I'm using the 2/3, isn't it? Kr is the kinetic energy. I'm multiplying that by 2 so that I get back velocities, and I'm dividing it by 3 so that I get the average. So then I have 2/3 Kr delta ij. That's what is the anisotropic residual stress tensor. And then what I do is the isotropic part, okay, I lump it into the pressure, because pressure is isotropic. It has no dependence on direction. So the isotropic part, I lump it into pressure. So I'm defining this P bar again as P bar plus 2/3 rho Kr. Instead of using a new notation, I'm just using the same notation and lumping the isotropic part of the residual stress tensor into the isotropic pressure, right? And I have this newly defined pressure P bar, calling it again P bar. Okay, so with that done, then I have now my filtered conservation of momentum equation as d bar t of uj bar is equal to nu del squared uj bar del xi minus del xi of tau ij small r and minus 1 over rho del xj of P bar. This includes the isotropic part of the residual stress tensor. This is the anisotropic part of the residual stress tensor. This is obviously the viscous term, and this is the substantial derivative of the filtered velocity, which is defined as del t of u bar dot del. We did the same thing for, we called it a mean substantial derivative at that time when we were deriving the Reynolds equations. These are the filtered equations. So now you have a filtered substantial derivative based on the filtered velocities, which is del t plus u bar dot del. Okay, so that is what we have, and as you can see, what we have on the left hand side is closed. On the right hand side, the first term is the viscous term. We know that because we know the filtered velocity. The rightmost term, which is the filtered pressure, we know that we'll get that from the Poisson's equation. The only unknown term is this one here, the residual, the anisotropic part of the residual stress tensor. Really, that is what we have to close. That is the term that we have to close here. Okay, it is at that point that the subgrid scale tensor comes in. A residual subgrid scale model comes in at that point. This is what is inside the grid. Follow me. This is what is inside the grid. These are the small scale motions that are not resolved. These represent the small scale motions or the residual motions that are not resolved, and we will need a model for that. We are modeling those. Isn't it? That's the premise of an LES. So Like the Reynolds equations for U mean, the filtered equations for U bar are unclosed, and closure is achieved by modeling the residual stress tensor or the subgrid scale stress tensor tau ij small r. Okay, now the filtered equations obviously are very different from the Reynolds equations. One, the main aspect, the most important point is the fact that the fields involved, U bar, P bar and tau ij small r, these are all quote unquote random, right? Seemingly random. They are 3D and unsteady. Even if the flow is statistically stationary or homogeneous, we are modeling the transient equations here, unlike the Reynolds equations which model steady state. So that's one thing. Secondly, the stress tensor to be modeled depends on the specification and type of a width of the filter, isn't it? So we haven't introduced that yet, but you will realize it later that tau ij small r depends on actually what type of model we use, what type of filter we use, and the width of the filter. So with tau ij given by a residual stress model or a subgrid scale model, the governing equations can be solved then at that point to determine what U bar is and P bar is. Of course, P bar comes from the Poisson's equation. The filtered velocity depends on the type of filter, the filter width, delta, and the type of filter, isn't it? So that you will see that the velocity actually depends on these quantities. But then, in spite of that, these quantities do not directly appear in the equations. That is because it comes in the specification of tau ij small r, which we'll see that later on how we apply the subgrid scale model. So I hope this is clear. So now that we have looked at the continuity and the momentum equations in the filtered context, let's look at conservation of energy. All right. So, and there's a reason why we are doing that, because the whole idea of coming up with an approach like LES was to resolve all the large scales where most of the energy is concentrated, right? So it is imperative to talk about the conservation of energy. And an important issue here is the transfer of kinetic energy between the filtered velocity and the residual fields, isn't it? Because here, unlike what we had in Rand's approach, we are resolving only the large scales and modeling the small scales. We know that according to an energy cascade process, the energy gets transferred from the large scales to the small scales. So how are we handling that transfer of energy? So that's an important issue that needs to be addressed. So for that, let's consider the filtered kinetic energy first. And what we do is, if your kinetic energy field is given by this equation, E of xt is equal to half u dot u, then your filtered kinetic energy is half u dot u bar, isn't it? That's your filtered kinetic energy. Now let's say I split that into two, meaning let's say I split the filtered kinetic energy into two, and EF plus KR. EF is this kinetic energy of the filtered velocity field, so that is u bar dot u bar, and Kr is this residual kinetic energy which we had defined earlier, which is half u dot u bar minus half u bar dot u bar. Okay, so that's the same as half times the trace of the residual stress tensor, isn't it? This is the trace of the residual stress tensor. Okay, so that is your residual kinetic energy. So what I'm doing is I'm splitting the filtered kinetic energy into like a kinetic energy of the filtered velocity fields and a residual kinetic energy. Okay, so EF plus KR. Now, I can obtain a conservation equation for EF by just multiplying the filtered momentum equation. Where is the filtered momentum equation? This one here. All right, this is the filtered momentum equation. Filtered momentum equation, isn't it? I can multiply this by ui, okay, and what I get is, remember, I multiplying it meaning dot producting it with ui, and then what I actually uj, because here what I need is uj dot uj is what I need, isn't it? So I need del t d dt of uj dot uj, and that is what I'm doing. So I'm dot producting it with uj, and then what I get is d dt of ef on the left hand side, and then what I'll have is, in each of these terms I'm going to dot product with uj or multiply it with uj, isn't it? So then what I get is, I'll bring in the viscous term here. So I'll have del xi uj 2 nu sij bar minus uj times tau ij r minus p bar over rho delta ij, and what I'm left with is these two terms related to dissipation and production, with the dissipation term given by 2 nu sij bar and the production term given by tau ij r sij bar. How did I get that? Because what I'm doing is, if I'm multiplying this by uj, okay, I am multiplying this tau ij term by uj, and now I have uj times del xi of tau ij r. I can write this as, okay, del xi of tau ij times uj minus, isn't it, minus tau ij r times del xi of uj. Tau I, so I'm just using the chain rule. I do the same thing here as well. Okay, when I multiply by uj, I take one of the derivatives out, and then you will notice what I get here. I will have del xi of this uj times one of the derivatives can be written as the strain rate, and then minus uj times tau ij r, which I showed earlier how I get that, and then minus the pressure term as is. So I'll have uj times p bar over rho delta ij. Then the left out terms, I take it to the right hand side. And then what I have is epsilon f minus pr. So epsilon f is this 2 nu sij bar, which is going to be the dissipation, and then this production term, which is tau ij small r times sij bar. So interestingly, what I have is d dt minus del xi of this whole term, okay, and I have these two sink terms on the right. One is a dissipation term, which makes sense, right? And the other one seems like a production term, but it is negative. So it seems like a sink term, isn't it? So let's think more about that. So the terms in the LHS of the transport equation shown above, they obviously represent transport, isn't it? Here, all of these terms represent transport, because we are talking about d dt of kinetic energy, which is equal to del xi. So that is a transport term because it is del xi. So it will be a transport term. But what we are interested in is the right hand side term. So we have a source and a sink term. The sink term, which is epsilon f, represents viscous dissipation directly from the filtered velocity field. Okay. Now think about it. We are choosing a filter width in the inertial subrange, which is much larger than the Kolmogorov scale. So how much will the dissipation be? We are talking about dissipation in the filtered velocity field. This filtered velocity field is associated with large scales. We have already learned earlier that the dissipation is kind of negligible in the large scales. It starts to be more active when viscosity starts to be more active at the small scales, closer to the Kolmogorov scale. So that means with a filter width being much larger than the Kolmogorov scale, this sink term is going to be negligible, relatively small. It could be neglected, for instance, but anyway, it is going to be small. The final term in the production equation, I'm sorry, not the production equation, the final term in the transport equation shown above, which is PR, is the rate of production of the residual kinetic energy. Okay, it's the rate of production of the residual kinetic energy. How do I know that? Because look at this term. Okay, it is tau ij r times sij bar. It has to do with the residual kinetic energy, isn't it? So that means it is the rate of production of the residual kinetic energy. But this term appears as a sink. Why? Because of the negative term in the equation for ER and as a source in the equation for KR. Okay, sink as an equation for EF. Sink in the equation for EF and as a source in the equation for KR. that means it represents the rate of transfer of energy from the filtered motions to the residual motions. So this is that term that represents the transfer of energy from the filtered motions to the residual motions. I hope this is clear. I want to repeat this. It's very important. The final term in the RHS of this transport equation here, okay, you have a negative there, which means it seems like it is a sink term. So it appears as a sink, yes, in the equation for ER. In the equation for EF, I'm sorry, I keep saying ER, but in the equation for EF, and as a source in the equation for KR. So therefore, it represents the rate of transfer of energy from the residual motions, from the filtered motions to the residual motions. All right. So this PR term is sometimes called subgrid scale dissipation and is sometimes denoted by epsilon s. But that terminology is inappropriate because unlike true dissipation, PR is entirely due to inviscid inertial processes, isn't it? And it can be negative. Look at this term. It is due to inviscid inertial, it has nothing to do with viscosity. It has nothing to do with viscosity. So calling it a dissipation, a subgrid scale dissipation, is technically not correct. It has to do with, it is a sink term, yes, but it is entirely due to inviscid processes. At high Reynolds number, with a filter being in the inertial subrange, this filtered velocity basically pretty much accounts for the entire energy, almost the entire kinetic energy. We had the number earlier where it accounted for about 80%, more than 80% of the total energy. So that means you're just neglecting the 20%, 15 to 20% of the energy. So in that sense, EF is approximately equal to E, isn't it? The average of this EF is approximately equal to E. So that means what? That residual kinetic energy almost does not exist, right? So then the dominant sink in the equation for EF is PR, whereas that in the equation for E is the rate of dissipation of kinetic energy, epsilon. So by that token, this PR is going to be equal to epsilon. Follow me? Because what we are saying is the filtered velocity field pretty much accounts for most of the kinetic energy. We had some number about 80 to 85%. So that means EF is equal to E, right? Approximately equal to E. So earlier when we split this, okay, into EF and KR, KR is almost negligible. The residual kinetic energy is almost negligible. That's the whole premise of LES, right? We are resolving all the large scales because we think that most of the energy is concentrated in the large scale. So why don't we just consider that? So then we are sort of ignoring the residual kinetic energy. So E bar is equal to EF. Now with that, if that is the case, the residual kinetic energy can be neglected. In that case, the dominant sink in the equation for EF is PR, okay, whereas that in the equation for E is the rate of dissipation of the kinetic energy, epsilon. So under that circumstances, basically PR, the production term, is equal to the dissipation. So whatever is the transfer, okay, is equal to the dissipation, because keep in mind the dominant sink for EF is PR, okay, whereas in the equation for E, the rate of dissipation, it is the rate of dissipation of kinetic energy, which is just epsilon, and that PR has to be equal to epsilon. You understand what I mean? Okay, so in the next class, what we are going to do is we are going to be applying the Smegrinsky model to all of this. Now, because we haven't looked at specifically what kind of subgrid scale model we'll use. We have looked at a general framework of a subgrid scale model, but we haven't looked at specifically what. And we will discuss specifically the Smegrinsky model in the next class and try and see how the equations apply. So what we have done here is today is we derived the filtered equations. Right? We looked at the filtered continuity equation, the filtered momentum equation, and then we looked at the conservation of energy. So we split split up the energy into two parts, as in the energy of the filtered velocity fields and the residual kinetic energy, and we realize that the residual kinetic energy is negligible, so that can be ignored. So that means whatever is the transfer from the filtered velocity field to the residual field is just dissipated, is approximately equal to epsilon. That was our final conclusion here. We will look at the development of the Smegrinsky model and how that applies to all of these concepts in the next class. Thank you.